So in this video, I want to go over the difference between a formal charge and an oxidation number. So if you were to analyze each atom in this molecule, you'll see each atom has a formal charge and an oxidation number. For example, this nitrogen has a formal charge of +1 and an oxidation number of -2. This nitrogen has a formal charge of 0 and an oxidation number of -1. So if you were to analyze each of these atoms, they would each have a formal charge and oxidation number. So what's the difference between formal charge and oxidation number, and how do we determine these values? Well, first let's go over formal charge. So to determine the formal charge of an atom, all you have to do is use a very simple equation. The formal charge of an atom equals the number of valence electrons it should have based on what the periodic table tells us versus the number of valence electrons it actually has. So let's try an example. Let's find the formal charge of this particular nitrogen. So to determine the formal charge of an atom, we need to use this simple equation, where we find the number of valence electrons nitrogen's supposed to have and subtract it by the number of valence electrons it actually has. So we see, due to nitrogen's location in the periodic table, it's supposed to have 5 valence electrons. So nitrogen is supposed to have 5 valence electrons. However, if we count the number of valence electrons nitrogen actually has, it's 1, 2, 3, 4. And the rule of thumb is if there's a bond, then the electrons are split between the two atoms. So again, this nitrogen we see has 1, 2, 3, 4 valence electrons. So it actually has 4 valence electrons. So plugging in these values in this formula, we get a formal charge of +1. So this nitrogen has a formal charge of +1. Let's try another example. What is the formal charge of this nitrogen? Well, again, due to the location of nitrogen in the periodic table, nitrogen is supposed to have 5 valence electrons. However, if we count the number of valence electrons this nitrogen actually has, we have 1, 2, 3, 4, 5. So this nitrogen actually has 5 valence electrons. And again, the rule of thumb is if there's a bond, the electrons are split between the atoms. However, there's a lone pair of electrons. These electrons all belong to this nitrogen. So if you count the number of valence electrons nitrogen actually has, it's 5. So therefore, the formal charge of this nitrogen is 0, plugging it into this formula. What about the formal charge of this carbon? Well, again, due to carbon's location in the periodic table, carbon is supposed to have 4 valence electrons. However, this carbon actually has 5 valence electrons. 1, 2, 3, 4, 5. So plugging in those values into this equation, we see this carbon has a formal charge of -1. What about this carbon again? Carbon's supposed to have 4 valence electrons. However, this carbon actually has 4 valence electrons, counting the electrons in these bonds. So plugging into this formula, we see this carbon has a formal charge of 0. So again, if you found the formal charge of this nitrogen, you would get a formal charge of +1. And if you found the formal charge of this carbon, you would get a formal charge of -1. And this formal charge actually tells us about the atom's net charge. For example, if this nitrogen has a formal charge of +1, that means it has 1 more proton relative to electrons. And in fact, this nitrogen has 7 protons and 6 electrons. However, this carbon has a formal charge of -1. So therefore, it has a net negative charge. And it actually has 1 more electron relative to protons. And this carbon has 7 electrons and 6 protons. So this formal charge really tells us about the net charge that that atom has. Also, something important to realize is if you add up the formal charges of every atom in a molecule and add up all those formal charges, you'll get the net charge of that molecule. For example, if you found the formal charge of this carbon, you would get a formal charge of 0. The formal charge of this oxygen, you would get a formal charge of 0. The formal charge of this hydrogen, you'll get a formal charge of 0. And the formal charge of this oxygen, you would get a formal charge of -1. So now that we know the formal charge of every atom in this molecule, if you add up all those formal charges, you'll get the net charge of this molecule. So we see the net charge of this molecule is -1. Also, something important to realize is when it comes to formal charges and radicals, you really shouldn't intertwine those two concepts because they're really separate concepts. Because we know whenever an atom has a single electron in an orbital, it's a radical by definition. However, what are the formal charges of both of these molecules? Well, if you found the formal charge of this oxygen, you would get a formal charge of -1. If you found the formal charge of this oxygen, you would get a formal charge of 0. So in this example, we see this ion has a formal charge of -1, but this radical has a formal charge of 0. But that's not always true for radicals. In free radicals, for example, this superoxide anion radical, this oxygen is a free radical, but it has a formal charge of -1. So really, you should separate the concept of formal charges and radicals. Sometimes radicals have formal charges of 0, and sometimes radicals have formal charges of -1. So really, they're separate concepts. Now I want to talk about oxidation numbers. So if you were to look at each of these atoms in this molecule, they each have their own oxidation number. For example, this nitrogen has an oxidation number of -2, this nitrogen has an oxidation number of -1, this carbon has an oxidation number of 0, and etc. So each of these atoms have their own oxidation numbers. But how do we determine these oxidation numbers? So to understand what an oxidation number is, we need to understand what electronegativity is. And we know electronegativity increases as we go in this particular direction in the periodic table. So as we go to the right and as we go upwards, the electronegativity increases. And we know electronegativity is an atom's tendency to pull negatively charged electrons towards it. So we can see fluorine has a very high electronegativity, while some of these atoms down here have a very low electronegativity. So therefore, fluorine, because it has such a high electronegativity, strongly pulls negatively charged electrons towards it. So now that we understand what electronegativity is, something important to realize is whenever there's a bond between two atoms, they're essentially playing tug of war. They're essentially trying to pull those negatively charged electrons towards them. However, the atom with the higher electronegativity will win and will pull those negatively charged electrons towards it and will essentially hog all those negatively charged electrons and will get a partial negative charge. So the key concept with oxidation numbers is to realize that whenever there's a bond between two atoms, they're fighting for the electrons, and the atom that's more electronegative will steal and will win and will pull those negatively charged electrons towards it. So the oxidation number essentially tells us how many tug-of-war battles that particular atom has won. For example, what is the oxidation number of this particular nitrogen? Well, let's analyze this particular nitrogen. We see this particular nitrogen has a tug-of-war battle with this hydrogen, and it has two tug-of-war battles with this nitrogen. So we can see, due to the electronegativity trends in the periodic table, we can see nitrogen is more electronegative than hydrogen. So therefore, in this tug-of-war battle, nitrogen's going to win. So it's going to steal those negatively charged electrons. So that's one negatively charged electron it's won. And it's also going to win this battle. So that's another negatively charged electron it wins. However, nitrogen has the same electronegativity as this nitrogen because they're both nitrogen. So both of these tug-of-war battles are draws. So we see this nitrogen won two tug-of-war battles. So it has a formal charge of -2. What about this particular nitrogen? So analyzing this particular nitrogen, we see it has 3 tug-of-war battles, 2 with nitrogen and 1 with carbon. So clearly these 2 battles are going to be a draw, but this battle, nitrogen's going to win because we know electronegativity increases as we go in this direction, so nitrogen's more electronegative than carbon. So nitrogen's going to win this battle, so it's going to win that negatively charged electron. So it has an oxidation number of -1 because it won that negatively charged electron. So what about this particular carbon? Well, we see it has 4 tug-of-war battles, but every tug-of-war battle is with another carbon. So every single one of these tug-of-war battles is going to be a tie. So therefore, this carbon has an oxidation number of 0. It's won 0 battles and it's lost 0 battles, so it's going to have an oxidation number of 0. So what about this particular carbon? Well, we see this carbon has 4 tug-of-war battles. And we can see, due to the electronegativity trends, we see oxygen is more electronegative than carbon. So because oxygen is more electronegative than carbon, we see oxygen's going to win that battle. So because oxygen's going to win that battle, it's going to steal a negatively charged electron. So because it's stealing a negatively charged electron from carbon, carbon's going to have a positive 1 charge. This battle is going to be a tie because carbon's the same as carbon. But what about these two battles? Well, again, oxygen is more electronegative than carbon. So this battle, oxygen's going to win. Oxygen's going to steal that negatively charged electron. So that's another positive 1 that this carbon gets. And again, same thing with this bond. Oxygen's going to win, so it's going to steal another negatively charged electron. So that's another positive charge. So again, whenever an atom wins a battle, it gains a negatively charged electron. But if an atom loses a tug-of-war battle, it loses a negatively charged electron, so it gets a positive oxidation number. So this carbon, we see it loses 3 battles, and it has 1 tie. So this carbon has an oxidation number of positive 3. So whenever you're determining the oxidation number of an atom, there's a couple rules of thumb. For example, group 1 atoms usually have an oxidation number of positive 1. Why? Well, we know electronegativity increases as you go to the right, so therefore these atoms in group 1 have a very low electronegativity. So they almost always loses battles. So because they always lose battles, they lose those negatively charged electrons, so they usually have an oxidation number of positive 1. And because they're in this particular row, they usually lose 1 electron, because once they lose 1 electron, they resemble an octet. So that's why these group 1 elements usually always have an oxidation number of positive 1. Positive because they always lose the battle, they lose the negatively charged electron. And positive 1 because they usually lose 1 electron, because once they lose 1 electron, they resemble an octet. And it's the same idea with these group 2 atoms. These group 2 atoms have low electronegativity, so they always lose the battles. But they usually lose 2 electrons because once they lose 2 electrons, they resemble an octet. So that's why they usually have an oxidation number of positive 2. So what about hydrogen? Well, usually hydrogen has an oxidation number of positive 1. Because remember, electronegativity increases as you go to the right, so therefore hydrogen has a very low electronegativity, so it almost always loses the battle. It almost always loses the negatively charged electron, so therefore it has a positive 1 oxidation number. However, the only exception is when hydrogen has a bond with a metal, because these metals have even lower oxidation numbers. So if hydrogen is bonded to a metal, then maybe it'll win the battle, and then it'll have an oxidation number of negative 1. So really the way you should think about it is with organic molecules, hydrogen usually has a positive 1 oxidation number, but inorganic molecules with metals, hydrogen will have an oxidation number of negative 1. Also, something important to realize is ions, like this bromide ion, will have the oxidation number that equals its formal charge. So this bromide has a formal charge of negative 1, so it has an oxidation number of negative 1. And also neutral atoms usually have an oxidation number of 0. For example, helium gas is neutral, so it has an oxidation number of 0. So a very simple rule is that fluorine is the number 1 most electronegative atom in the periodic table. So therefore, fluoride always wins the battle. It doesn't matter if fluoride is bonded with hydrogen, carbon, nitrogen, fluoride always wins the battle. And due to its position in the periodic table, it usually has 1 bond. So therefore, fluoride usually has 1 bond that it wins. So therefore, fluoride almost always has an oxidation number of negative 1 because it usually has 1 bond and it's always more electronegative, so it will always win that 1 bond. So it will always win that negatively charged electron and will have an oxidation number of negative 1. The only example where this isn't true is when fluorine is bonded to another fluorine. If fluorine is bonded to another fluorine, this tug-of-war battle is a tie, so fluorine will have an oxidation number of 0. It doesn't win or lose any electrons. So what about oxygen? Oxygen is similar. Oxygen is the second most electronegative atom. So oxygen almost always wins the battle. And also due to oxygen's location in the periodic table, it almost always has 2 bonds. So because oxygen almost always has two bonds, and it almost always wins both bonds, it's almost always going to have an oxidation number of -2. Because again, oxygen almost always has two bonds, and it's almost always more electronegative, so it'll win both electrons. It'll win this electron and it'll win this electron. So therefore, it almost always has an oxidation number of -2. So that's another rule of thumb. Oxygen almost has an oxidation number of -2. So again, oxygen almost always has an oxidation number of -2, but there are a couple examples. For example, if oxygen has another bond with another oxygen, this bond's going to be a tie. So nothing's going to happen with this bond, but this bond oxygen's going to win because oxygen almost always wins. So it's going to win this negatively charged electron, but this bond's a tie. So therefore, in this example, this oxygen's going to have an oxidation number of -1. One bonded wins, so that's -1. And this bond's a tie, so that has no impact. And also, I don't know if this molecule actually exists, but if oxygen had two bonds with the fluorine, then in this example, oxygen would lose both battles. Because again, oxygen is the second most electronegative atom, so it almost always wins. The only time when it doesn't win is if it has a bond to fluorine. So again, fluorine is the single most electronegative atom. So therefore, in this case, oxygen is going to lose both of these battles. So it's going to lose both of these negatively charged electrons. So when it loses one negatively charged electron, that's +1. It loses another negatively charged electron, that's another +1. So that's a net oxidation number of +2. So now that we know these rules of thumb when it comes to oxidation numbers, now we can solve for the oxidation numbers in these polyatomic ions. But something important to realize is if you add up the oxidation number of all these atoms in this polyatomic ion, it will equal the formal charge, the net charge. So we see this polyatomic ion has a net charge of -1. So knowing that, we can determine the oxidation numbers of all these atoms. So again, we know oxygen almost always has an oxidation number of -2. However, we can see we have 4 of these oxygens. So each oxygen has an oxidation number of -2, but we have 4 of them. So that's a total of -8. So this oxygen contributes -8. We see the net charge is -1, so therefore this manganese must have an oxidation number of +7. Because remember, if you add up the oxidation number of all the molecules in a polyatomic anion, they will equal the net formal charge. So therefore, these oxygens contribute -8. Manganese must be +7 because that's the only way we can get a net charge of -1. So what about this compound? So we see this has a net charge of 0. So knowing this, what is the oxidation number of all these compounds? Well, again, oxygen almost always has an oxidation number of -2, but we have 4 of them. So oxygen contributes -8. We see potassium is a group 1 element, and we see group 1 elements always have an oxidation number of +1. So therefore, if oxygens contribute -8 and potassium contributes +1 and the net is 0, then we see chlorine must be +7. This chlorine must have an oxidation number of +7. What about this example? So this is a tricky example. So we see the net charge is -2. That's the formal charge, the net charge. So if we add the oxidation number of all these compounds, it must equal -2. So again, we know oxygen has an oxidation number of -2, but we have 7 of them. So these oxygens contribute -14. Each is -2. We have 7 of them. So these oxygens contribute -14. And remember, hydrogen is a group 1 element, which are almost always +1. But we have 2 of them, so that's +2. So what is this phosphate? Well, what's the oxidation number of this phosphate? Well, again, we see the net charge is -2, and we have a +2 here and a -14 here. So therefore, we can infer that this phosphate must contribute -10. And that's the only way we can have a net charge of -2. Hydrogens contribute +2. All these oxygens contribute -14. So therefore, these phosphates must contribute -10. And that's the only way we can have a net of -2. Because remember, the oxidation number, when you add the oxidation numbers of all these atoms, it must equal the net charge. So therefore, these oxidation numbers must equal the net charge of -2. So therefore, phosphate has to have has to contribute negative 10. But again, we have two phosphates. So if two phosphates contribute negative 10, each phosphate must be negative 5. And that way, there's two of them, so they contribute negative 10. So the point is, whenever we're analyzing an atom in a molecule, it has a formal charge and it has an oxidation number. And these formal charges and oxidation numbers don't always match. For example, this nitrogen has a formal charge of 0, but this nitrogen has an oxidation number of negative 1. And so there are different processes to determine the formal charge and the oxidation number, but hopefully after this video you have a better understanding of the difference